Okay, so today is a continuation of yesterday. So just the quick plan for today. So yesterday, most of you who are here, we saw what is Boolean function analysis on the Boolean cube, and we saw what it is good for. And I mentioned that also it's sometimes a good idea to consider Boolean function analysis beyond the Boolean cube. So now I'm going to explain what I mean by beyond the Boolean cube. And there will be two main generalizations. One of them is to association schemes, and the other one is to differential posets. And if I have time, I'll mention some other generalizations. Okay? So we will start with association schemes. And actually, we will not be considering general association schemes because this is a computer science talk, so we're not interested in the most general thing possible. Rather, we'll consider a specific type of association schemes that come from graphs. And in the association scheme literature, these are known as metric association schemes or p-polynomial association schemes. Okay, so a metric association scheme is a finite distance regular graph. Okay, so this is kind of a dictionary explanation. So I'm explaining one term by another term, which maybe you don't know, although I explained it yesterday. So for all I, j, and k, there exists a constant n I, j, k such that if x and y are vertices at distance, let's say k, then the number of vertices at distance I from x and j from y is nijk. Okay, so again, so if I give you two numbers, I and j, and I give you two vertices, x and y, and I want to know how many vertices are at distance I from the first one and j from the second one, then this only depends on the distance between the two original vertices. Okay, this is a distance regular graph, and this is the same as a metric association scheme. Okay, so it's a pretty simple definition. Our running so I'm not sure who was the first. It got popularized, you might say, by Desart, but probably wasn't the first.
What does it capture then? Associativity. Something that's analogous to a group, you can share some properties
with the Boolean groups, yeah. I don't think so. No. Yeah, there's a more abstract definition that I won't get into. Yeah, because we want to be concrete. So there's also a definition where this distance function doesn't come from a graph. But otherwise, but we do have this property. So this is the more general definition.
So this captures associativity in some sense.
Yeah, and we'll see it in a minute when we get to the Bose-Messner algebra of the scheme. But before that, just... Yeah. Bose, okay. But the association schemes I'm going to mention is from a list made up by Desart in the context of coding theory. Okay, so our running example is going to be the Boolean hypercube. So this is a 0, 1 to the n, or plus minus 1 to the n. And we connect two vertices if they differ in one symbol. So the distance between two vertices is just the same as the Hamming distance. And this is also, so another name for this is the Hamming scheme. And we'll get to it later. So why does the...
Transitive graph satisfied because you have automorphism that sends that replaces vertices, or maybe not.
Right, so...
Stronger. The distance regularization.
maybe two transitive graph. Yeah.
But it's rare.
Yeah, there's in some sense, if you also add another property, which I'm going to explain in a few later on, then there is sort of a list of all association schemes in some sense. Not really, but to some extent. Okay, so because of what Chai says, it's maybe not so difficult to see that the Boolean cube is a distance regular graph. Okay, due to this symmetry, and you can also, if you really want, you can work out this number Nijk. It's written in my notes, but I think it's pointless to actually write it. So something having to do with the binomial coefficients, yeah. Okay. So this is a metric association scheme. This is the basic object we're going to discuss, and some examples. We're going to get to it later in more detail, but the slice is an example. So this is the set of the subset of the Boolean cube containing all vectors of with a fixed histogram, with a fixed number of ones. The Grassman scheme, so the subspaces is also an example. We'll get to it later, yeah. Okay, but before that, that's why they have this thing.
Yeah, you were here, you know. It's a parallel depression. No, you can.
Yeah.
You can do them both in parallel.
But I'm not into distributed algorithms, so. Okay, so now I'm going to define the Bose-Messner algebra of a scheme.
What do you mean? It's a centralized algorithm.
Okay, so this is the collection of all V by V matrices. And let's call an example matrix A such that A of X and Y depends only on the distance between X and Y in the graph. Okay, and this is similar to, or rather, it's a generalization of what are known as circulant matrices, if you've heard of them. Yeah. And also for the circulant matrices, this is a directed graph in here, yeah. So it's not quite the same, but it's very similar. Okay, now why is this Bose-Messner algebra called an algebra? So it's, yeah. Okay, so clearly it's closed under addition and scalar multiplication. So it's a vector space, and it's also closed under multiplication. Why is that? So let's say that A of xy is some alpha of the distance between x and y.
Only for a strongly ordered?
Yeah, it's equivalent. And v of xy is beta of the distance between x and y. And now we're going to look at, let C be A times B. Then, so what is C at the point xy? This is sum over all z of A x z b z y, which is sum over all z of alpha of the distance between x and z, and beta times the distance of z and y. Okay, now because this is a strongly regular graph, then I know exactly how many terms of each kind I have. I only need to know the distance between x and y. So this thing depends only on the distance between x and y. Yeah, I can write out the entire formula, but the board is too small, the margin is too narrow. So I won't do it, but, and you can see this is probably equivalent, for connected graphs or whatever. Yeah, I didn't mention here, but it has to be, as there, it should be a connected graph. If it's not a connected graph, then this is a coherent configuration. Some of you might have heard about this in the context of matrix multiplication. Okay, so the Bose-Meissner algebra is an algebra. It's an algebra of matrices. It's closed under multiplication, and it's also commutative. You can see this also from here, because the distance is commutative, basically. Okay, so what do we know about commutative algebras of matrices? They have common eigenspaces. And how many of them? So what is the dimension of this algebra? So the dimension of this algebra depends on like the possible values of this thing. So it's 1 plus the diameter. Okay, and this also gives us the number of common eigenspaces. Okay, now I'll give an example. Yeah, everything is over the real numbers. If you're a mathematician, you search the most general setting. I'm content with working over the real numbers, or maybe the complex numbers. It's good enough for me. Yeah, so now in the particular case of the Boolean hypercube, so if the graph is the Boolean hypercube, yeah, and you can see it from the formula here, because distance is symmetric. Yeah, and this is like in some sense there's some representation theory hiding here, and it's not a generalization of groups. It's a generalization more specifically of abelian groups. There's something abelian going on here. This algebra is abelian, and in some generalizations, the algebra won't be abelian, and then the theory becomes not as nice, and people care about it much less for some reason. Some non-symmetric matrices, I don't think you like them too much. Yeah, we have here an expert in direct combinatorics, so I don't know what people actually study, but I mean, it does make sense when you do abelian groups. So, for example, circulant matrices are not symmetric. Okay, so if the graph is the Boolean hypercube, then the common eigenspaces are, so maybe somebody wants to guess what the common eigenspaces are? Okay, so there are n plus 1 eigenspaces. Yeah, the degree d something. So there Vd, which is the span of, so if this is plus minus 1 to the n, span of the functions, these functions, what I called xs yesterday, for all s of size exactly d. Okay, so you can do this calculation. It's not so difficult, so we'll skip it, but it's pretty easy to check that this is actually the case. And now we can define the degree of a function using this decomposition. So this is really, we have this orthogonal decomposition of the space of all functions over the cube. This is a direct sum of these VDs. Okay, so if I give you any real valued function on the Boolean cube, then you can consider its projections on these different VDs. This is what I called yesterday the f to the equal d. Yeah, now we can define so given an ordering, can you read this? Yeah. An ordering VI of the common eigenspaces, then the degree of a function f on the scheme is the maximal d such that the projection of f to Vd is non-zero.
So sometimes it will be more interesting to order than great distance.
Yeah. So we'll see in a minute. Some orders are better than others.
There's no definable order like in the Boolean system. Canonical.
Well, there is. That's the point of yeah.
Products are integrated, right?
Yeah. Yeah. Okay, but before we get into this, so just yeah, so you can say that the function has degree d if it lives in the span of the first d plus 1 common eigenspaces in the fixed ordering. Okay, this is an equivalent way of saying the same thing. Okay, now on the Boolean cube, and what we have is that the degree, that's what Zev said, of f times g is at most the degree of f plus the degree of g. Okay, and we call an association scheme, a metric association scheme with a specific ordering that satisfies this property, we call it Kko-metric or Q polynomial. Okay, so now to answer Shai's question, in most cases, if the association scheme is Kko-metric, then there's a unique way to arrange the subspaces so that this happens. But in some exceptional cases, there are two ways, and I think these are understood perfectly. There's a monograph by Banai and Ito called Association Schemes 1. There was no Association Schemes 2, but it's also out of print. It's very difficult to get a hold of, like they don't have it here. I think maybe in the university, but not in the institute. And there you have the specification of all the, what they call P polynomial association schemes with two Q polynomial structures. But usually, there's only one way. Yeah, sure. And for a random association scheme, there's probably no way. But because we're doing Fourier analysis, and we really want there to be a notion of degree, and so we will only consider Kko-metric association schemes. Okay, so now what I'm going to do is, yeah, questions? Now what I'm going to do is I'm going to give a few canonical examples of association schemes and talk a bit about each of them. And then I'm going to talk a bit more about specifically the slice, which is just what I was interested the most in. Just doesn't always work.
It's all in the list. Is this in any way that captures all the commutative matrix algebras?
I seriously doubt it.
So the question is every commutative algebra of matrices coming from a...
Like a coherent configuration?
I don't think so. Just something I...
I think it's very easy to make commutative algebras. Like when you choose a basis, take diagonal matrices, forget it.
So there's something I forgot to mention. With each association scheme, you can associate two matrices, P and Q. One of them is, so you take the matrix, which contains ones exactly when the vertices have distance I, and now you consider its eigenvalues, and you make a matrix out of it. So this is, I think, called P, or maybe it's called Q, and the other one is the inverse of. And if you look at these matrices, then you find all these nice orthogonal polynomials. And particularly for the case of metric and cometric association schemes, then there's a theorem of Leonard, which gives you a list of all of these, all the possible matrices. So in this sense, all of them are known, but there's sometimes two different association schemes with the same parameters. Like for the experts, there's twisted Grassmannian. So in some sense, we do know everything, and in some other sense, we don't. Yeah.
I'm not sure if this is a basis to set of this, but it's very natural to look for nice basis for this, not just basis for the eigenspace, just basis for the algebra. And one is where you take matrices which are 0, 1, just like zeros except those x, y for which the distance is something. They satisfy the algebra, and that's one Boolean basis. There's another basis that it's made out of PSD matrices. That's very useful too.
Yeah, that's the projections to the projections for to the VIs. So there's a very nice theory, and there's some duality between matrix multiplication and pointwise multiplication. But I'm not going to discuss this because I have other things to discuss.
But what I want
Yeah.
to say at the end of my sentence,
Yeah.
this shows up in a lot of places, but also in some of Square's
Mm-hmm.
shows up very useful.
Yeah. That's
Really everybody is super interested.
Like Traveshi.
Kapchuk polynomials.
It's extremely hard to remove association from a proof in the...
Yeah, I can say you get these association schemes because of symmetry, because in many situations you're interested in matrices which satisfy some symmetry properties, and then they belong to the Bouillon algebra, and then you know they're eigenspaces. So that's where it all comes in. But I'm not going to discuss this.
These two bases you mentioned are some abstraction of the Fourier basis and the, I don't know.
No, so this corresponds to the coarse decomposition.
The PSD one corresponds to the
PSD was projections on the eigenspaces, right?
Hmm?
yeah. And the first one, the Boolean one, is like you have unit vectors.
Yeah, yeah.
These are the natural unit vectors.
I think also in a given case, you could say that the base, the coarse decomposition is one-dimensional. In that you can actually
Mhm.
write also the sum of, expand in terms of characters,
Mhm.
while for these other association schemes, you cannot expand in terms of characters.
Right, but here we don't see the. We want to abstract away the characters. We want to think only of the coarse decomposition because we don't have this nice basis in general. Yeah, we'll get to it when we talk about the slice. Okay, just if you look at the literature, then this spatial basis is called AI, and this PSD matrix, which is known as the central idempotence for some reason, this is called EI. So now if you see it in the literature, then you're Like the only thing you're missing, this is pointwise multiplication. Now you can read all the literature and enjoy. Yeah. Okay, so some famous association schemes. So okay, and these association schemes are all metric and co-metric, so they have a notion of degree. So we have the Hamming schemes, the Johnson schemes, the Grassman schemes, and the bilinear scheme. Okay, and this is a picture which you can find in some papers of Desalt. So he made up this list of important association schemes, and I'm now going to go over them one by one. Okay, so the first scheme, this Hn of m, it's a generalization of the Boolean cube. So here, the vertices are Zm to the n. And you connect two vertices if they differ by one coordinate. Okay, so the distance between two vertices is just the Hamming distance. Okay, and when m equals 2, then you got the usual cube. And here, like Professor said, here we can actually, we have something beyond just this coarse decomposition. We have an actual Fourier basis, so this is kind of, for me, boring. Yeah, so whatever you can do on the Boolean cube, you can probably also do here. Maybe you'll need to work a bit more, but it's basically more of the same. Okay, then we have the Johnson scheme. And maybe I should write the names. So this is Hamming. And this is going to be Johnson. So this is related to the Johnson graph and to the Kneser graph, which are both members of the Bose-Messner algebra of the. Okay, so here the vertex set is the set of all subsets of the numbers 1 to the n of size exactly k. Or you can think of it as a set of all 0, 1 vectors of length n with exactly k ones. And you connect two of them if their symmetric difference is 2. Or if you think of them as sets, if their intersection is k minus 1. Okay, so the distance between two sets is k minus the size of their intersection. Okay, and I'm going to talk more about this later, so I'm not going to say anything more now. Yeah, yeah, St. Johnson scheme, yeah. Yeah, so, right. Yeah, so this is an obstruction for graph isomorphism. Yeah.
So then you connect the vertices with the distance to the
yeah, minimal distance, yeah. So like this is induced by yeah. It's even like Fedon calls it coordinate induced, because there are coordinates here which correspond to coordinates here.
But you cannot take any subset and induce it in the
No.
Two layers and square the graph.
Okay, so now we have the Grassman scheme. Okay, so now Q is a prime power. We only care about Q equals 2, but it makes sense for any prime power. And we have here a vector space of dimension n over fq, and we look at the collection of all k-dimensional subspaces. And we connect two of them if the dimension of their intersection is k minus 1. Okay, now the reason we use the same notation is because this is the Grassman scheme is the Q analog of the Johnson scheme. Now there are some people who have some formal definition of what it means to be a Q analog. But for us, there are lots of quantities that you can count. For example, the size of the scheme, number of vertices. And this is some rational function in Q. for fixed n and k. And when you take the limit q equals 1, then you get n choose k. Okay, and there's some people who think they know why this happens. Other people disagree with them. Anyway, this is the Q analog of the Johnson scheme.
There are lots of theorems in combinatorics where you first of proof for sets, which is like this, and then generalize for some work.
Yeah.
It's a natural tendency of combinatorics.
What are the directions?
Also, but it's much. It's usually, the Pescador Theorem,
Yeah.
theorems in extremal combinatorics where non-trivial there, maybe even less trivial in some cases.
So in this counting thing, you said that there is a way to take this rational function that determines n choose k, then take the limit as q tends to 1.
Yeah.
Is there also a way to get a reasonable definition of jq and k for q between 1 and 2?
For q between 1 and 2.
It's like a vague expression, so you can drop it if there is.
So I know in some circumstances it does make sense to formally consider q, which is arbitrary, just use the same formulas, whether it corresponds to anything in the real world.
It's not clear that you get a structure. You may get a number, but it's not clear that you get a structure.
Right.
Yeah.
So I was wondering if there is some tensor of construction that corresponds to q being between 1 and 2. Anyway, yeah, sorry.
Okay, and just to complete the picture, we have the neglected bilinear scheme. So actually, I'm saying neglected, but actually this is what is used in the recent work on the 2-to-1 conjecture. So here we're looking at, so this is the bilinear scheme. And we're looking at n by m matrices over fq. These are the vertices, and we connect two of them if they differ in rank 1. And fq. Yeah, but we only care about q equals 2. Yeah, it's our favorite prime number. Okay, and generally the distance between two matrices is the rank of the difference. Okay, it's somewhat neglected in the literature, but maybe not anymore. There is a nice basis here, which looks like the basis here, which is why it's so much easier to work with. Whereas here, it's a big mess.
The JQ is some modding out HQ by some own action of some other.
Yeah, I'm going to talk about it. Yeah. But before I talk about the connections between the Grassman and bilinear schemes, let me just mention some generalizations. So there's something called polar graphs. Maybe you know about them. Some expert tried to explain to me the definition. I didn't quite understand it. It's some sort of generalization which is very natural from the point of view of the theory of buildings. Yeah, so these are things which are like the Grassman scheme. And there are also things which are like the bilinear scheme. So we can consider, let's say, only symmetric matrices when n equals m, or Hermitian, or whatever. So these are some other examples of association schemes which people care about to some extent. Okay, now for the relation between the Grassman scheme and the bilinear scheme. So first of all, the direction which is used in the paper, if I use m equals k, then usually, unless k is very close to n, then the vectors here are going to be linearly independent. Yes?
M is less than k.
Yeah.
So m is less than n. You take m equals k.
Oh, yeah, it should be.
M is k, right?
Yeah. Okay. And because the rows are linearly independent, they're going to define an m-dimensional subspace. Okay, so this is something that maybe algebraic combinatorics would not consider because it doesn't happen for all the points, only for almost all the points. But we in computer science, we like probability theory, so it's okay for us. And this is the connection which is used in the proof of the 2-to-1 conjecture. So instead of working directly here, which is a big mess, they work here, which is not such a big mess. And also they in some sense, they add self-loops to the graph. So yesterday I explained, now we have the notion of degree, but yesterday I also mentioned that we have a total influence and the noise operator, and they can all be defined just given the graph. So to get the cleanest possible numbers, then you have to add self-loops for the bilinear scheme.
With the same weight or higher weight?
The correct weight.
The
correct
You
weight.
want a random walk, but it's like a laser random walk is probability half its
So you want, so the eigenvalues of the Laplacian are close to powers of 2, and if you add the self-loops, then it will be exactly powers of 2. Yeah. Okay. And there's also a way to go in the other direction to realize the bilinear scheme as a subset of the Grassman scheme. This is known as the attenuated space construction. So you look at J, Q, n plus m, m, and you consider and you fix some n-dimensional subspace of this n plus m dimensional space, and you consider everything here which has trivial intersection with this n-dimensional subspace. And what you get is the bilinear scheme. Okay, so this is some relation in the other direction. Okay, now a few more examples. So one example of an association scheme which doesn't come from a graph is the perfect matching association scheme. There are two n vertices, and we look at all the perfect matchings on these two n vertices. Okay, and our notion of distance is just not going to be an integer. So we're going to take the two perfect matchings and put them together on one graph, and then we're going to count how many cycles of each length. And this is our notion of distance. And this satisfies... yeah, right. That's what I'm saying. So it's not a number, it's a vector, but it satisfies this property that the Bose-Meissner algebra is a commutative algebra. So this is...
The distance function, the way you defined it before, distance function doesn't have to be a single integer. It can be a vector of integers.
So...
equation. There is no inequality between the vectors.
Yeah. So this is an...
Depends on the distance. The distance can be any value.
Right. It doesn't really have to come from a graph. So the actual definition is you have...
It doesn't have to be a number of distance. Distance can be a couple of numbers.
Can be whatever you want, an abstract set. Yeah, an abstract set. So the actual definition of association schemes is for every pair of elements you need to come up with a number. There must be a number which you always obtain when you take two identical elements, and you only get it when you have two identical elements, and there's some symmetry. I guess it should be symmetric. Depending, there's even a more general notion, but usually we only consider the symmetric case, and this is the more general definition. But we are mostly interested in association schemes which come from graphs. No, it's an abstract set.
Is the dimension of this dx1 related to the copies of irreducibles that appear in the eigenspaces?
Yeah, so... Okay, so another way to construct, let's say, the Johnson scheme is you take the group Sn, and you look at its Young subgroup Sk times Sn minus k, and you look at the collection of all, let's say, left cosets or right cosets, depending on whatever you prefer. And this is going to be, the points here are going to be isomorphic to the Johnson scheme. If you look, so this is a representation of Sn, because there's an action of Sn on these things. And if you look at the decomposition into ERPs, then each of them appears at most once. Okay, and this is why this Bose-Meissner algebra is commutative. And when this happens, when you have a group and a subgroup, and each ERP appears once, this is known as the Gelfand pair. Okay, so now you know the theory of Gelfand pairs. And you can also realize the Grassman scheme this way. So now you have to start with a general linear group, and you have to take what's known as a polar subgroup. Okay, and now if instead of this Sk times Sn minus k, you take a product of more than two more than two symmetric groups, then there will be some multiplicities. And then it's no longer an association scheme, so people doing association schemes stop caring.
So perfect matching of your example of
There, I think you have a wreath product. Yeah, I'm not sure it's exact. Well, yeah. So this is going to the S2 times S2. Yeah, yeah. So that would be an example of that. Yeah, maybe we'll get to it later. Okay, so what I'm going to do now is I'm going to talk a bit about what is known about the slice in particular. And then we're going to talk about what is the correct way to study these things. And then we're going to have a break and talk about differential posets. This is the plan. Okay, so this will be more about the Johnson scheme J and K. Okay, and this goes by the name Johnson scheme, but you can also call it the slice because it's a slice of the Boolean cube. This is maybe like the colloquial name. Okay, and now what I'm going to do is we will start with the fundamental theorem of Boolean function analysis on the Johnson scheme. Okay, so what did this theorem say about the Boolean cube? So every function on the Boolean cube, plus minus 1 to the n, has a unique representation as a multilinear polynomial. A multilinear polynomial. But this is no longer the case on the Johnson scheme because, for example, so if you think of it as a set of all 0, 1 vectors with k1s, then the sum of all coordinates minus k is 0. So you can represent 0 as the sum of everything minus k. And also, if you compare dimensions, then there's no way it could work. So there's the fundamental theorem, which is due to C.P. Dunkel, or Dunkel. It was an American, so probably said Dunkel. So every real-valued function on J and K has a unique representation as a multilinear polynomial P of degree at most the minimum between k and n minus k, which is harmonic, which is not what you think. So harmonic means that if you sum all the formal partial derivatives, then you get 0. Okay, and I give examples in a moment.
This is in your fit. Or this over the real, so this over the real.
You can also think of it as a formal derivative. Yeah. So an expression which is equal to the function on all points of the scheme. Yeah, this is not like a presentation from representation theory. It's
the bounded degree is the number of eigenspaces,
right. Yeah.
And this is true over anything?
Yeah.
So it's like the right number of equations, so that this gives
right? And they're all independent. Yeah, yeah. Okay, yeah, so before giving some examples, some people object to this adjective harmonic because usually it means something else. But I found this in some book, so it's not my fault. Just copied it from somewhere. Yeah, so examples. So the polynomial 1 is harmonic. X1 minus x2. X1 minus x2 times x3 minus x4, and so on. Right, you're laughing, but this is actually, there is a very important examples, because if you take the span of all of these examples, then you get V0, V1, V2, and so on. And these are exactly the common eigenspaces.
Products of different sets of disjoint pairs.
Well, you want them to be multilinear, so.
No, not disjoint as sets. Oh, they are disjoint as sets.
Yeah.
Okay.
Yeah, so now maybe some intuition why we have these conditions, why they make sense. So we got multilinearity because xi squared is equal to xi. Right, so there's no reason to have powers because it's 0, 1. We have the bound in the degree, so let's say k is less than n over 2. So there's no reason to have any monomial of degree larger than k because it would just be 0. And this condition corresponds to the fact that the sum of xi is constant. Okay, now I gave an exercise to my students in class to prove this theorem, and I think nobody managed to do it. Yeah, it's not so. You can do it, but you have to sweat a bit. Yeah, so in contrast to the case of the Boolean cube, here there's actually something that you need to do. So this is already an indication how things here are not as simple as over the Boolean cube.
The main thing is to prove that non-zero polynomial like that can also represent a zero.
Yeah.
So the values of this x just become 0 and 1 in this case, right?
Yeah, it doesn't. I don't think it makes a difference because we always take the difference of two things. Oh, okay, so if it's plus minus 1, you get xi squared equals 1. Yeah, and in general, if you right, yeah. But still, the theorem will still be true if you choose any two values. It doesn't really matter. Okay, now something which is not as nice is that these functions, okay, so any function, let's say here, is orthogonal to any function here because these common eigenspaces are orthogonal. So here when I say orthogonal, it's with respect to the uniform distribution over the Johnson scheme. But if you take any two functions here, they're not necessarily going to be orthogonal. And if you want an actual orthogonal basis, you have to do something. So there's the general theory of Grassman and Zetlin, a new approach to the representation theory of Sn. And using this, you can read off an explicit orthogonal basis for the scheme if you really want to, but it's not that useful. Yeah. Yeah, so.
You multiply you have the same pair, it will cancel it, but you have.
So there's something to prove here.
Right.
So what you have to prove is that if you have some function which can be represented by some polynomial of degree d, then there's also another representation of degree at most d of this form. So you have to prove it. It's not obvious. So if you take this ordering of the common eigenspaces, then you get the cometric association scheme. So this gives the correct notion of degree. And you also have this nice property, like we had for the Boolean cube, that a function has degree d if and only if it's a linear combination of d juntas, where d junta is a function depending on d coordinates. And this is something that you also have for the Grassman scheme. Okay, so this is the fundamental theorem. I'm sorry, it makes a huge noise. Yeah.
I'm wondering out loud whether it's still true that the function of degree d will depend on a junta on, I don't know, from 2 to the d.
Yeah, excellent. So this was resolved, see, January, I think. So if k is very, very close to d, then, like, for example, if k is at most d, then you can't say anything. It's the parameter k here, close to, like if k is very, very small or very, very close to n. But what we can show that if k is between, let's say, 10 to the d and n minus 10 to the d, then a Boolean function of degree d depends on its most cd coordinates, where cd is the same constant you get on the cube. Okay, so now we'll have some famous theorems which have been generalized to the Johnson scheme. And this is going to be, I think, probably a complete theorem. Complete list. Okay, so we have the fundamental theorem. So this is due to Dunkel. And there's an explicit Fourier basis. This is really what is known as a Gelfand-Zetlin basis. So the thing about this basis is that it's not canonical. It depends on an ordering of the coordinates. And you can see that you can't get anything canonical because, let's say for V1, the dimension of V1 is n minus 1. So you can't use one function per coordinate. You need to use less. Okay, so this is due to Srinivasan, and due to myself separately, and due separately to Ambanis et al. And this is just the people I know of. Might be even more. And this is in the context of quantum computing, quantum group testing. So this shows up not only in sum of squares, but also in quantum algorithms. Yeah.
What was your motivation?
I like this stuff.
Stability theorem. It's the maximum theorem.
Originally, yeah. Yeah, this is something actually I neglected to mention. So the Erdős-Corrado theorem, this is a classical theorem in combinatorics. Yeah, the anecdote here is the paper is from 61, but Erdős claimed it was already known. They already proved it in 38, but they waited for a few years. So it states, probably. So the theorem concerns subsets of the Johnson scheme. And you want to know what is the largest subset of the Johnson scheme where every two sets are intersecting. So if k is more than n over 2, it's not interesting. And otherwise, then the best construction is to take one point and everything that contains it. When k is exactly n over 2, then you also have other constructions. But when k is strictly smaller than n over 2, then this is the unique optimal family. And then you can ask the question like, suppose I'm an intersecting family, and my size is almost this n minus 1 choose k minus 1. Am I close to an optimal family? And this is exactly the sort of situation which, for which theorems in Boolean function analysis are suited.
So this is a purely combinatorial statement, but you're saying that this tautology is very useful in this context.
Yeah, although by now we know that there are actually better ways to do it, and you can get better bounds if you do something else.
Stability theorem is when you have an inequality and it's achieved by some structure, you wonder if you are close to the inequality. Are you close to that structure? Right now we have many.
Yeah, so this was my original motivation. Yeah.
Stability.
By that, okay, so in that sense, isothermally pointed all stability.
Yes,
Yeah,
yes,
yeah.
absolutely.
I mean, you have robust versions, and this will be the. Yeah. Yeah, anybody who's interested in this, and there's a student of Nathan Keller, Noam Lifshitz, he knows how to prove all of these stability theorems. So just look at his archive page, and you can find, yeah. You can also ask him questions and get a paper written for you. Okay, so the next thing is the Kkl theorem. So just to remind you, on the Boolean cube, the Kkl theorem states that if you have a balanced function, then there is an influential coordinate, whatever that means. Okay, so there's a way for this to make sense even on the general Schreier graph, which is a generalization of Cayley graphs. I'm not going to get into it, but there is a very natural way to make sense of it, and there's a general proof of Kkl on Schreier graphs, which relies on hyperconductivity. So maybe this should be really 4. So this is due to Donald Wimmer. Okay, and hyperconductivity so just to remind you, so we define the noise operator, which is just a random walk on the scheme. Okay, this makes sense in any scheme. And now you want to have a result saying that if you start with a function, let's say of norm 1, and you take this random walk, then you also have LQ norm 1 for Q larger than 2. So you've somehow averaging over neighbors irons out all the bumps in your function. Okay? So this was proved by Li and Yao. What they actually did is prove a log Sobolev inequality, which is something really arcane from functional analysis / probability theory, but this is equivalent to hyperconductivity. And this is what you need to prove Kkl.
These are notions of expansional graphs in which you care about not how L2 changes, but entity.
Yeah, and this is, as somebody explained, it's a dimension-free inequality. So you get the same parameters, whatever n is. Okay, now you have Friedrich-Hunter theorem. And this is due to Wimmer and simplified by myself. So Friedrich-Hunter theorem states that if you have a function on the Boolean cube with small total influence, then you're close to a junta. And the same statement also holds for the slice in some settings of parameters. Yeah, and it's, or another way to look at it, it's invariant under permutation of the other coordinates. So there's some functions which are juntas depending on this, and also juntas depending on this at the same time. It could happen. So yeah, this is some complication that you need to deal with when you talk about juntas here.
Is this the same paper where Wimmer learns subspaces on permutation invariant distribution?
No, this is only this. Yeah. Okay, now we have the FKN theorem. So this theorem states that if you're a Boolean function which is closed in L2 to degree 1, then you're close to being a dictatorship, a one junta. And this is true when K over N is bounded away from 0 and 1. Okay, so this was proved by myself. We have the, I'm going to run out of space. But Kko Theorem. This is due to Kkl and Klein. So this states that if you have a Boolean function which is closed in L2 to degree d, then you're close to a junta. Yeah, this is very recent. I don't think you can find it online. You can, if you're interested, you can ask them. It's very nice. And
You have more theorems.
yeah,
You can erase some
Right.
famous theorems.
right.
It's already clear from the
Okay, so now we have invariance principle, which I'm going to speak briefly about. So this is due to myself and Kindle and Mosel and Wimmer, and also due to myself and Just Elchanan. And I'm going to talk about this in a bit. And finally, the question that I asked, Boolean degree d functions are juntas. And this is due to myself and Ferdinand Ihringer. Okay, I think there are a few other results, but yeah, this list is long enough as it is.
These proofs are usually similar to the original proofs once you have the decomposition.
So it depends. So for the Kkl theorem, it's very similar. It's basically the same. Here the idea is the same, but yeah, here it's basically also the same, but there's some calculations which are not so obvious. Here, I'm not sure how you would do it in the same way. And also here, they have to work much harder. This is a different statement, so a different proof. And here also, there are some tricks. So when k over n is, let's say, bounded away from 0 and 1, it's the same proof. But when k gets smaller, then you need to do something else. But this also happens on the Boolean cube. I'm going to talk about it in a moment. Okay, so before moving on to how to think about association schemes, I just want to talk a bit about the invariance principle, and then maybe we'll take the break. So the invariance principle, we are faced with the following question. So I give you a function on the slice, on the Johnson scheme, and I want you to give me a function extending it on the entire Boolean cube with similar properties, whatever that means.
Just on the Boolean cube, not on the...
Yeah, that's on the Boolean cube. Okay, and so there's a question of what is the correct measure to use. So now we can think of it as two different measures on the entire Boolean cube. The first one is a uniform measure on just the vectors of Hamming weight k. And the other one, we're going to pick the product measure with the same marginals. Okay, so for example, when k is n over 2, then we're comparing the uniform distribution over what is known as the middle slice to the uniform distribution over the entire cube. But when k is not n over 2, it's something else, then you need to take one of these mu p distributions. Okay. So we want the extended function to have the same values on the slice. No, well, you can't have it. No, we don't have to start with the Boolean function. It can be an arbitrary function. Similar properties. For example, you want maybe to have similar L2 norm. If you take the expectation of a Lipschitz functional, you want the empirical distribution to be similar. So if you take a random point and then apply your function, this gives you a random variable. And you want these two random variables to be similar in some, using some metric on distributions. For example, the CDF distance, which we don't know, or the Levy distance. or what Avi said also, if you decide from a Boolean function, you want to end up with a function which is close to Boolean in some sense, like in L2 sense. Okay, so you can't do it for a general function, but if your function happened to be to have small degree, then the correct recipe is to take your function on the slice, on the Johnson scheme, and now to use this unique representation, and now you can plug in whatever value you want. And then you can prove that these two functions are going to have similar behavior. For example, they're going to have similar L2 norms. They're going to, if one of them is Boolean, the other one is going to be close to Boolean.
The best possible way to do it also.
Yeah, and also it's a canonical way in some sense, which I don't remember, but you can sort of axiomatize what you want, and
It's somehow related to how GNM and GNP are similar, you know, properties, graph properties in GNM and GNP for P equals 1.
Yeah, yeah.
Because there we know that almost the same.
Yeah, but there it's
variable, but,
right. It's for monotone Boolean functions usually, and then it's easier. You get better bounds. Yeah. So this is a more general statement of this the same sort. Yeah, it's usually for monotone functions. Yeah. Yeah, it also makes sense for arbitrary graph properties, but more sense for in the monotone case.
By the way, about number 9, something doesn't make sense. So if you just take k equals 1, I guess there it's not correct.
No, so you need k to be at least in our case exponential in D. It might be also true for smaller k.
For k equals 1, any function is linear.
Right.
So it's not true.
Yeah. So certainly k has to be larger than D, and we can also have counterexamples showing that k has to be larger than like D plus 2 or D plus 3, depending on the parity of D. Okay. So now let's say that we're mostly interested in studying the Johnson scheme and the Grassman scheme and the Bilinear scheme. How are we going to do it, and what are the particular complications that we're going to have to contend with? Okay, so here there's a first step which is kind of a lacuna in the classical Boolean function analysis literature, and this is mu p for small p. Usually, like classically, when you do Boolean function analysis on the Boolean cube, then you do everything with respect to the uniform measure. But in some cases, you want to consider other product measures. So this mu p measure is the measure that gives every coordinate which is 1 a probability of p, and every coordinate which is 0 a probability of 1 minus p. And we usually think of p, which is at most a half. And this is very natural when you study Erdős-Renyi random graphs, because this GNP model is exactly this mu p distribution on the set of edges. Okay, so there's this Pescador theorem, and there is an analogous theorem for small p, which is known as a sharp threshold theorem. Okay, so the question is, you have this graph property, and you want to know whether at the threshold, whether it jumps really quickly from 0 to 1 or not so quickly. So let's say if you're containing a triangle, it's not so quickly, but for being connected, it's very quick. So you want to be able to tell, and the thing is that if it's not so quick, then in some sense you have low total influence, and then you can say something about the property. Let's say that it's correlated with small subgraphs. So these are the sharp threshold theorems. And this, I believe, is the only context in which people who are interested in studying Boolean function analysis on mu p for small p. Okay, so when p is a constant, which is not a half, let's say 1/3 instead of 1/2, then usually you take your garden variety theorem, and it probably generalizes without too much work, too much hassle, to p equals 1/3. But when p is close to 0, like subconstant, then some other phenomena emerge. So, for example, take the Friedrich-Lehner theorem, the FAN theorem, which states that if you have a function which is close, a Boolean function, which is close to degree 1, then it's close to a 1 junta. Okay, so now imagine that p is very small, and you consider the function the maximum between x1 and x2. So this function is very close to x1 plus x2. because the probability that you're going to see both 1 and 2 is very small. But it's not close to a 1 junta. Okay, so even this Fkn theorem is not true as stated for small p. The correct theorem is that you're always close to a maximum of like 1 over p different coordinates, or to a minimum. Yeah. Okay, and why is this important? So what is this p, and how does this relate to the Johnson scheme and to the, let's say, Grassman scheme? So in the Johnson scheme, or more generally, p is the probability that a specific point is inside the set. So for the Johnson scheme J and K, it's K over N. Now, maybe in some cases you're interested in K, which is a constant fraction of N, and then everything will be simple. But in applications to computer science, it turns out that you're often interested in relatively small K. And then you're in the small p regime. Okay, although there's this one instance where mu p is used. This is for the Dino-Safra paper, where they prove a hardness approximation result for vectors cover, and there it's mu p for constant p. But in all other applications, p is small. As another example, you can take the Grassman scheme, where you can think of each subspace as a collection of vectors. But the probability that each specific vector appears in this collection is really, really small. So you also expect to see things like you see in mu p for small p. Okay, so one thing which happens for small p is that you don't really have hyperconductivity. Or rather, you have some bound which is not so useful because it really deteriorates as p gets smaller. And then you expect to have these small sets which do not expand. Maybe. Okay, so it seems like the correct way to study these more complicated schemes, the first thing to do is to study Boolean function analysis on the Boolean cube, but with respect to the product measure mu p for small p. This would already capture some of the difficulty of these schemes. Okay, so now you do that, and now you study the Johnson scheme J and K, where K is the constant fraction of N. Okay, so now you won't have this small p phenomena, but you will have other phenomena because, for example, you don't really have a decent Fourier basis. Okay, so you do that. Now we can tackle the Johnson scheme with K small, which combines the difficulties of the previous two examples. And now you're ready for the Grassman scheme. Okay, in the Grassman scheme, you have this kind of duality that you don't really have for the Johnson scheme. So if I'm looking at J, Q, and K, then this is isomorphic to J, Q, and N minus K. You map V to V perp. Okay, so as an example, so if you look at the functions of degree at most 1, then they are spanned by the characteristic functions of containing a vector. Yeah, so if f is degree 1, then you can write f as sum of this form. So let's say f of v. So a sum over all vectors x, alpha x, of 1, x is in v. Okay, so this is this one representation, but you can also do it if you apply this mapping with beta y, 1, y perpendicular to v. Okay, so this is another different basis for functions of degree at most 1. Okay, and this is something that we don't have over the Johnson scheme. So on the Johnson scheme, this operation corresponds to taking the complement. What would correspond to y being perpendicular to v is y not contained in S, which is very similar to y contained in S. So it's not such a big deal. But here, these are really two different things. And why is this a mess? So let us consider what we saw before, the Grassman expansion hypothesis. So the claim was that if you have a small set which does not expand, then it has significant weight inside a copy of a smaller Grassman scheme. And you get this copy of the smaller Grassman scheme by identifying some vectors x and some vectors y, where you want to look only at subspaces containing the x's and orthogonal to the y's. But how do you know what you're looking for, if you're looking for x's or for y's? You don't know, because you have this duality, and like what you might try to do is you can represent your function using, let's say, this kind of basis, and then it will make it easier to find x's. Or you can do it this way, and it will make it easier to find y's. But if you don't know in advance, then kind of it's not really clear what to do. So in these recent papers, the way you move from the x basis to the y basis is by using Fourier transform over z2 to the n. So this converts between the two bases. And this somehow comes naturally from the proof, but I'm not sure like what is the correct way to think about this matter. So like not only do we not really have a Fourier basis, we also don't really have a good canonical representation, because we don't know if we want to look at x's or y's. Okay, so I'm not sure if this was very clear, but this is another complication that makes this Grassman's case specific, even more complicated than other cases. And this is also what made the argument more difficult. Somehow, when you move to the bilinear scheme, then things become nicer. Okay, so what I want you to remember from this discussion is that it's interesting to study the Boolean cube with respect to mu p with small p. Okay, so this concludes the first part of my talk. And in the second part, which is going to be much shorter, we're going to switch gears and to discuss differential posets. Or it's really formally sequentially differential posets. This is some invention of Stanley. Okay, so now we can all take a deep breath. Okay, now again we use the example of the slice. So we consider the Boolean lattice. Okay, so this will be a small example. Okay, and so this is a graded lattice. Okay, so we have a decent notion of depth. Yeah, but we don't care about this. Yeah, so that's what I mean by lattice, but really, I guess it's called differential poset for a reason. And maybe it doesn't have to be a lattice. We're going to consider some specific examples anyhow. Okay, so this is, as I said, a graded poset. And what this means is that you can assign to each point a depth. And now a point is strictly is above another point only if the difference in levels is 1. So like, yeah, layered graph, yeah. Maybe for every lattice. No, even not for every lattice. Yeah.
If it's an order, then you can just
No.
So again, what's the definition?
So
Why topological sorting then?
Yeah, I mean, suppose you have a triangle. A is less than B, B is less than C, and A is less than C.
yeah. So I don't want. Yeah. Okay. And now I'm going to define two operators. There's the up operator mapping PL to PL plus 1, and the down operator going the other way. Yeah, so it's defined for every level. Okay, so what does the up operator do? So you have a function on this layer, and to define it here, you just take the sums over all the edges. Yeah, and down is the same thing. No, over the reals. Yeah, okay, so.
You can do it over every real with a standard sign.
Yeah, so this is something very odd. So an example of this framework is high-dimensional expanders, which are high-dimensional analogs of expanders. A high-dimensional expander is a complex satisfying certain properties. And usually we study complexes using homology, and we have orientations. But when studying random walks, you don't want the orientations. So take everything you learned about complexes and just forget it. Yeah, this is very confusing. Why is in one setting it's really important to have orientations, and here it's really important not to have them. So this is for the experts. Yeah, so we don't have the orientations. Okay, now we're still working with the Boolean lattice, and let's see what happens when you take down and then up, or when you take up and then down. These are known as the upper and lower Laplacians. So we have a function f on, let's say, PED. So what is down, up of f at a point S? Okay, so if you go one level up and one level down, then first of all you get, yeah, so you get everything at distance 2. So you get this. But you also get your own set. Like you can go up and down and get to the same place. And how many times does this happen? N minus d. Okay, and if you go up and down, then you get this term. It stays the same. But here, instead of n minus d, you get only d. Okay, so as in conclusion, you get the. Possibly, yeah. It's a bit confusing. You won't care too much about this. So you get this identity. Okay, so if you're considering, now we're on level D, so the difference between du and ud is some scalar product of the identity. Okay, so if this happens to be the case for every level, this number could depend on the level, then we get what's known as a sequentially differential poset, or for short, differential poset. The actual definition of a differential poset is where these numbers are the same for all levels. But then the lattice has to be infinite. And we don't like infinite things. So an example is the Young lattice of all Young diagrams. Okay, now why is this of interest to us? Okay, so now let us consider some Johnson scheme J and K with K at most n over 2. And let's consider a function which lives in the highest common eigenspace. Okay, so consider a function f on J and K such that f is in Vk. Okay, so we know that there's a representation of f as a sum of well, as a homogeneous degree k polynomial. Yeah, so by the fundamental theorem, f is equal to a multi-linear homogeneous degree k harmonic polynomial.
The homogeneous was not clear from the theorem.
No, but I said that Vd is spanned by these functions x1 minus x2 times x3 minus x4 d times.
Yeah, but the fact that it's
Right. So there was another. Yeah.
anyway.
Yeah. So the decomposition into the common eigenspaces is exactly taking the homogeneous parts of this unique representation, just like in the case of the Boolean cube. Okay. And now what we can do is we can look at pk and write on each of the sets the value of the function f. Okay, and this is also the same as this polynomial. So let's say f is some sum of alpha s xs. So xs is just a product of xi for I and s. And then because it's homogeneous of degree k, then so s equals to k, then f of s is equal to alpha s. Okay? Okay, so now we have this function on pk, and how do we express the fact that it's harmonic? Okay. Maybe something on the board. So what's the sum of the... Yeah, yeah. So f is harmonic. It's the same as saying that df is 0. Okay, so we recover the notion of harmonicity from the post set. Okay, so this... So because we don't have the signs, what we actually need for this setup to work eventually is we want the up operator to have full rank. And we'll see in a moment. Okay, so this was for functions in Vk, but if we have a function in Vl for L smaller than k, then what we can do is we can take a function on the else level and then just take the up operator enough times. Okay, and then we'll get another function on the correct level. So every function on pk has a unique representation f sum of L from 0 to k of u to the k minus L fl, where fl is a function on pl satisfying such that dfl is 0. And this is more or less this decomposition into homogeneous parts. It's only more or less because when you take the up operator, then the value of the function gets multiplied, but we can ignore this. Okay. And now, how can we see using this this sort of stuff that these different parts are orthogonal? So this is where this this property is going to come in. Okay, so these up and down operators are adjoints. Okay, with respect to this inner product, which is the uniform distribution over the level. So now the claim is that UK minus L FL and UK minus R FR are orthogonal. So suppose you manage to find such a decomposition, then I claim that these different parts, they have to be orthogonal. So it has to be an orthogonal decomposition. And why is that? So that's, yeah, I think we need to assume that K minus L is larger than K minus R. So let's suppose that L is smaller than R.
It's not an assumption. One of the two happens.
Yeah. So choose the without loss of generality. Okay, so this is equal to, we move the U's to the other side using the fact that U and D are adjoint. Okay, and the point is that this number is larger than this number. Okay, and now what we can do is we can, whenever we see du, then we can replace it by ud plus something. And the way to think about it is either we switch their locations or we just drop both of them. And because there are more d's than u's, when we consider the tree of all possibilities, then we will always end up with the d all the way to the right, because there are more d's than u's. Okay, and because dfr is 0, then this is equal to 0. Okay, so now the more general claim is that if you have a differential poset and it satisfies some properties, there's a long list, and then there will always be a unique decomposition of this form. Okay, so one example is the Boolean cube, and another example is its Q analog, the Q cube. So what is the Q cube? So now you have some finite field FQ, so Q is a prime power, and you consider all the subspaces of this dimension n vector space over FQ. And you construct a similar, oops, I erased it, but a similar poset. And now the same theory will work, and we get the analog of the harmonic representation to the Grassman scheme, for the Grassman scheme. You can think of all of this as some kind of generalized inclusion-exclusion. Okay, we have the important property which comes up in some proofs that the up operator has a full rank. And the way to see it, so because you know that this is true, then du is ud plus this thing. Now we know that ud is positive semi-definite. So for d, which is smaller than n over 2, when you add to ud this n minus 2d, then all the eigenvalues become strictly positive. So du is positive definite, and so u has full rank. And this is like this huge trick that can be used to prove the fundamental theorem for the slice, for the Johnson scheme.
So it's not quite like inclusion exclusion because again you don't have the minus. You don't have the, it's not like the minus. It has more to do with the fact that the functions we care about, functions on the slide, are have the sign minimum basically because of.
Yeah, but the signs come in from the property that it's in the kernel of D. So you need to have the signs.
Yeah, I see. So you say it's equivalent. Is
I mean, more generally speaking, if you do representation theory FSN and you construct the EREPs, the Young modules, then this is really glorified inclusion exclusion. So.
For the Grassman scheme,
So you certainly have this canonical representation, which is just a harmonic multilinear polynomial of the correct degree.
harmonic is the sum of the subspaces zero.
This is exactly the same construction as you get it from here. I think there's also some kind of well, yeah, I believe there is something which is like a Fourier basis. So I didn't explain what it is for the slice. Maybe I'll have some time later. Probably not, but.
Even just for the Q cube, I mean, there's a Fourier basis.
So there are some papers with some nice bases. So yeah, probably. So it's fair to say that so far people haven't really looked that much into the Grassman scheme from this perspective. So as an example, then, so on the slice, the degree D function is a junta, unless k is like really small. We don't know this on the Grassman scheme. So this is something very basic.
If you don't care about the slice,
Yeah.
the entire Q cube.
Uh-huh.
You get here nice interesting theorem.
Of an entire Q cube. So there are some papers of Srinivasan which are relevant here. People have thought about it, some people. Yeah, I think there are some nice things you can say. Yeah. Yeah. Okay, so I don't have that much time left. So first of all, let me mention that you can do this this theory along the lines of differential posets also for high-dimensional expanders. So what is a high-dimensional expander? Yeah, you can think of it as a poset where it's not really differential because du minus ud is not exactly a scalar, but it's close to a scalar. So this is one property of high-dimensional expanders. Another property is that if you look at this du and ud operators, then they have nice eigenvalues. Okay, as I said, I should say this is just one type of high-dimensional expanders. There are other types. And this is apparently useful for constructing PCPs, apparently. Okay, so this is where the theory of high-dimensional expanders ties into general Boolean function analysis. Okay, so in the remaining time, so when should I finish? Okay, so actually I have a lot of time. Okay, so that's all I really wanted to say on differential posets. Yeah. So we think of it as a function which lives on PL. And you can also think of it another way to think about these things. It's not exactly the same, but it's similar that this is just this function corresponds to monomials in this polynomial representation. So with each point in the poset, we associate a function on pk, which is 1 when you are above this this point. Okay, so this is not exactly the same as taking the up operator enough times, but for a sufficiently regular poset, it will only differ by some scalar multiple. So this is the other way of thinking about it. And if you want to define harmonic, then these two viewpoints are the same. Okay. So now I would like to briefly mention some other settings where you can hope to do a similar sort of Boolean function analysis. So this would be part 3. Okay, so the first example is quantum Boolean functions. So this is from a nice paper of Montanaro and Osborne. So in quantum computing, we usually care about unitary matrices, but here it seems the correct thing to look at is Hermitian matrices. So if you look at all 2 by 2 Hermitian matrices over the complex numbers, then the dimension over the real numbers is 4. And there is some basis for this space over the real numbers, which is famous in physics. It's called the Pauli basis. Okay, and this gives you an analog of the Fourier expansion for 2 to the n by 2 to the n Hermitian matrices. Yeah, so this is really another Q analog of the Boolean cube. And you can define just about anything. You can define degree, you can do influence, a noise operator, you get hyperconductivity. So there is some noise operator which is a quantum noisy channel, something from quantum information theory. Now you can ask, so I have this theorem in Boolean function analysis, do I have some analog in the quantum world? So first of all, what is the correct analog of a Boolean function? So if you have on the Boolean cube a plus minus 1 valued function, f, then it satisfies f squared equals 1. And you can do the same in the quantum world. So you want your matrix to be a root of unity. And then because it's also Hermitian, then it's unitary, and actually all of its eigenvalues are plus minus 1. Now, one way to get these functions is just to take diagonal functions. And these are like the classical functions which are not entangled. But there are also many other examples. So this is a quantum Boolean function. It's 2 to the n. Hmm? Yeah, it's not really a function, it's a matrix.
Yeah. No, the function is from n qubits
Yeah.
to
Mhm.
a qubit.
Well,
Like from 2 to the n space, like matrices of size 2
Mhm.
to the n to 2 by 2 n. But these are the functions you are talking about.
so the functions are really operators. So it's an operator on the space of n qubits.
Okay, but it's an operator, and what's the
We don't have a value.
No. When it is Boolean, if the square of it
Is 1. So if all the eigenvalues are plus minus 1. Yeah. So this is the definition, and it's a good definition because you can prove, let's say, some version of, I think, the Kkl theorem for this definition. So actually, because you're doing quantum computing, then you can either do L2 stuff or you can do L infinity stuff, which for some reason makes a lot of sense in quantum. So you actually have at least 2 potential versions for every theorem, one with respect to L2, like in the usual case, and the other one with respect to L infinity. So Montanaro and Osborne, they had this nice paper where they do lots of stuff, and then people sort of forgot about this. And now nobody ever considers it. I don't know why. People told me, yeah, there's so much else to do, so, so much stuff, so little people, so few people, so we can't be expected to do everything.
What was the motivation of Montanaro Osborne?
Quantum PCP theorem. This should be the motivation. So Boolean function analysis is very, very useful in understanding classical computing, classical complexity theory. So if you want to understand quantum complexity theory, maybe it's a good idea to develop a Boolean function analysis in its quantum analog. Yeah, so this is one thing which will be great to do. Another nice example is the short code. So this is Fourier analysis on codes. So this is work by a bunch of people. I'll read you the complete list. Like all the papers by Boaz, it's lots of people. Barak, Gopalan, Hostad, Mekar, Gavendra, and Stoirer. Yeah, these are the people on the short code paper. So the idea is to take an error-correcting code. They want it to be locally testable, so we want the dual code to have low-weight code words. So what we do is the vertices are going to be the dual code, the points in the dual code, and the edges correspond to this low weight points in the dual code. And then specifically for the case of the Reed-Muller codes, they show an invariant principle which relates this thing to the entire Boolean cube. And it's very nice. And they also think maybe this generalizes to other locally testable codes. But at that point, they lost interest because, you know, Reed-Muller codes were enough for their applications, but this seems very intriguing. Yeah, so you take a locally testable code, C, and now you're constructing a Cayley graph where the points are the dual code, C perp. And you connect 2 points if they differ by a low weight vector. So you choose low weight vectors, which are the way you locally test the code. So these are your edges. It's a Cayley graph. Yeah, nice, yeah.
In the Reed-Muller case, you take all degree D polynomials, and two-degree D polynomials are connected if their difference is the product between outcomes.
Yeah, it's a very nice paper.
Yeah. And these guys, what they did?
So they prove some kind of invariance principle from which they derive some kind of majority stablest. Yeah, what does it mean? We have the expert.
The main motivation of the paper was to reduce a counterexample to ABS.
I don't think. I think the main, we want to construct better PCPs with better parameters, like smaller PCPs.
Yeah. So the long code, the main disadvantage of the long code is reduction for hardness estimation because it's long. So you're losing the parameters of the hardness estimation. So you want to, so what's the long code? It's all possible functions. You want a smaller set of functions. Smaller set of functions. You take the low degree polynomial. It's roughly exponentially smaller. And it has, for the testing that happened in PCPs, is approximately as good. And this is what you need to do.
Yeah, so I invite everybody to look at this paper. I haven't had the time, but so they need to get, let's see, majority stablest. I'm not sure. So this invariance principle is the same as saying some pseudorandom property of the code. Yeah, I don't want to say wrong things. So yeah. Okay, and the last example is we have continuous spaces like Gaussian space. And tori. So this is the plural of torus. It's a product of many circles. Okay, and these are examples where, so first of all, we are interested in Gaussian space specifically because of the classical invariance principle, which relates the Boolean cube to Gaussian space. But also in these spaces, then there is a natural noise operator. So in Gaussian space, it's Brownian motion, and on these tori, it's the heat semigroup. And you could ask for analogs of theorems on discrete spaces for these spaces. And indeed, there's a student of somebody in France. The student's name is Raphaël Bouilly, professor I forget. And apparently, there are some theorems in Boolean function analysis, which you have the theorem for the Boolean cube, you have it for the Johnson scheme, and you also have it for, let's say, Gaussian space. And in some sense, the proofs are all the same. Or more accurately, they're analogous. And you can, like, so the thing you cannot do is you cannot really have a meta proof for which these are all special cases, but it does seem like the methods are very, very analogous. So you might want to extend Boolean function analysis to these continuous spaces. Okay. As an example, then there's this paper of Kot and Moshkovitz, which suggests a way toward the unique games conjecture using reals. So this might have some relation. Okay, so I think that's enough for today.